Let's start by talking about some properties that conductors have when they're in electrostatic equilibrium, and then we'll get back to Gauss's law. The first thing we know about a conductor that's in electrostatic equilibrium is that any excess charge that's added to that conductor ends up on the outermost surface. Why is that? Because like charges repel each other, and a conductor, the charges are free to move around. So they're going to move as far away from each other as they can. They're going to end up on the outermost surface of that conductor. The next thing we know is that the electric field is zero inside of a conductor that's in electrostatic equilibrium. Electrostatic equilibrium means the charges are not moving. And if the electric field wasn't zero, the charges would be moving. There'd be a force on those charges. F equals QE, right? If there's an electric field present, a charge in that electric field feels a force. And if that charge is free to move, it's going to move. So the conductor wouldn't be in electrostatic equilibrium then. Like, for example, the wires in the walls of our house that carry our electric currents. When we turn the electricity on, there's an electric field present inside that conductor, and the charges move because of it. But they're not in electrostatic equilibrium. So if we know it's in electrostatic equilibrium, if the charges have stopped moving, we know the electric field has to be zero. The next thing is that the electric field is perpendicular to the surface just outside the surface of the conductor. That has to be true because the charges aren't moving. If the electric field wasn't perpendicular at the surface, if it had some component that was tangent to the surface, then an electron at the surface would move. It would feel a force because of that component of the electric field. So the electric field can't have any component tangent to the surface. It has to be completely perpendicular to the surface if the charges aren't moving. The fourth thing is that surface charge density is not uniform everywhere on an odd-shaped conductor. Where the radius of curvature is the smallest, the charge density is actually the highest at that point. Where the radius of curvature is larger, the charge density is less. And we'll learn about this next chapter. Let's talk about how we use Gauss's law when we have an infinite sheet of charge. First, let's understand what the electric field looks like in that case. Let's say I just have a point charge. The point charge sends electric field out uniformly in all directions, and we get an electric field that looks something like this. Now, instead of having a point charge, if I could spread that charge out and make it look like a little bit of a line charge, the electric field would take on this shape. So at the center of this rod, as I stretch out that point charge and turn it from a point charge into a short rod, at the center, the electric fields start to come out parallel to each other, but they deviate pretty quickly and start to spread out. But if I could take my rod and spread it out, make it even longer, let's see what happens. If I could spread that charge out over a longer rod, the electric field at the center of that rod would look very uniform. And as we moved away from the center, we would see those lines starting to spread out the way I drew it. Now, if I could make that rod infinitely long, let's see what would happen. So my rod now extends to infinity in each direction. That's what my little dashed lines there mean. Now what happens is the electric field looks like this. The electric field lines align and become parallel to each other, and we don't have any edge effect. Oftentimes students will say, well, why do we learn about solving for the electric field next to an infinite rod or an infinite sheet? There's no such thing. But really, it's not a bad approximation, because if we have a long rod, it doesn't have to be infinitely long. If we want to know what the electric field is very close to the rod, even if it's only as long as my pencil, if we want to know the electric field just a few millimeters away from the pencil, it looks like an infinitely long rod if you're only a few millimeters away from it. So if you're interested in the electric field in this region right here, we can kind of approximate that like an infinite rod. And the same with a sheet of charge. So the rod, of course, we're looking at this rod from the side and we're seeing the electric field lines line up like this. If we look down from the top, they would still come out radially from this rod. But the same thing happens with a sheet of charge. With a sheet of charge, this happens in both dimensions. Not only does it happen when we look at it from the side like this, but if we shift and look down from the top, we would also see parallel electric field lines if this was an infinite sheet of charge. So an infinite sheet, I'm going to attempt to draw in 3 dimensions here. My infinite sheet of charge is perpendicular to the page, and it's got charge on it. Let's just make it positive charge. And it sends electric field lines out from it in this direction and also in this direction. And those electric field lines are parallel to each other if this is truly an infinite sheet of charge. If it goes to infinity in both directions, then these electric field lines are parallel to each other. The electric field is uniform. It's constant everywhere near this sheet. When the electric field lines get farther apart or closer together, that tells us the electric field is changing. It's getting stronger when the electric field lines get closer together, and it gets weaker when the field lines get farther apart. But if the field lines are parallel to each other, they never get closer together, they never get farther apart. That means the electric field is constant. So we know 2 techniques for finding the electric field from a charge distribution. We can treat each little tiny element of charge like a point charge, and our point of interest would be out here somewhere. We want to know what's the electric field at that point. And we could find the contribution to the electric field at that point from this little point charge, and then we integrate all from negative infinity to positive infinity in this direction, and from negative infinity to positive infinity in this direction. We integrate over that whole sheet and add up all the contributions. And this gets a little ugly. It's not terrible, it gets a little ugly. So let's see if Gauss's law can help us here. We have some symmetry, right? These electric field lines are uniform, they're parallel to each other. So if we could put some kind of a shape in here where the sides of our shape are either parallel or perpendicular to the electric field lines, well, it might be a useful thing to use Gauss's law with that shape. One shape that would work would be a rectangular box. We could put a box in here. I'm going to try to draw it. like that. That's the best I can do. So now we could use that shape as our Gaussian surface. There are 6 sides to a rectangular box, and we could integrate the integral of E dot dA over all 6 of those sides and come up with an answer. But usually we like to take this other shape. Usually we like to take a cylinder. And how would we orient our cylinder? With the axis parallel to the electric field. Otherwise, it doesn't help us with the geometry of this situation. So we would want to put our Gaussian cylinder oriented along the electric field lines. Either one of these shapes would work as our Gaussian surface. I'm going to use the cylinder. So I say the integral of E dot dA over all sides of that enclosed surface, this imaginary shape I'm imposing on my problem, is equal to the charge inside the cylinder over our constant epsilon naught. So my cylinder has 3 surfaces to it. It has this left surface over here, and it has the right surface over there, and then it has the curved side to it. The integral over the left surface of E dot dA plus the integral over the curved side of E dot dA plus the integral over the right side of our cylinder. I think that covers everything. Is Q inside of our cylinder over epsilon naught. Right, all of this is what makes up that integral. When you see that circle there, it means over all sides of the enclosed shape. The left side is perpendicular to the electric field. So this is just the electric field times the area times the cosine of 0 degrees, which is 1. The curved side, the electric field never penetrates it, right? It just skims along the top. So that gives us 0. There's no flux through the curved side because we have a cosine of 90 degrees. The electric field is pointing along the surface, but our area vector, of course, points perpendicular to the surface. So no electric field lines penetrate that. They all skim along the surface. None of them penetrate the surface. So the flux is 0. And the right side gives us E times A times the cosine of 0 degrees. Remember, the area vector points outward from our surface. And the electric field is also pointing outward from the surface. That's why I have a 0 degrees for both the left side and the right side. So what do we end up with? 2EA is equal to Q inside over epsilon naught. And what A is that? That's the area of the end cap here. The area of that circle that makes up the end of my cylinder. Now I need to figure out Q inside my cylinder. Well, the cylinder is intersecting that sheet in a circle. And I would have to be given the surface charge density of my sheet. So let's pretend our sheet has a surface charge density sigma, that's given to us. Sigma would be given in the problem. Now I can figure out how much charge is inside of my cylinder in this green area here. It's the area A multiplied by sigma. And the area cancels out. And that makes sense because it's an arbitrary dimension of our Gaussian surface, and it shouldn't depend on that, right? If I pick an area that's small and you pick an area that's large, we should both end up with the same answer for our electric field, some distance away from the sheet. The electric field is sigma over 2 epsilon naught. The interesting thing here is that there's no dependence on distance. Remember, we sort of knew that already, right? Those electric field lines are parallel. When I say they're parallel, I mean they're parallel. They do not diverge or come closer together. They are parallel, which means the electric field has to be the same everywhere as you move away from the sheet. And you might wonder, how could that be? How is it that the electric field's not stronger when I step up closer to the sheet of charge? And the reason is that if you have a sheet of charge over here, I'll just make it positive, and you're very close to it. Let's say we want to know what's the electric field right here. You have to remember the electric field is a vector quantity. So some of this charge, you're quite close to it. And it's going to create an electric field here that's pretty strong. But as you start to move away from the center, what happens if we're really close to this sheet? The electric field from some charge up here is pointing almost parallel to the wall. And there's an equal charge down here that creates an electric field pointing this way. And those two y components, if we're calling that direction our y direction, the y components cancel out. And all we're left with is a tiny contribution from the x components. So those almost completely cancel out. Not quite. They've just a little bit of contribution from the x component. And the closer you are to the wall, you see that all that charge that's far away, it's almost all canceling out. Now, as you move away from the wall, the charge at the center, this stuff at the center, is not contributing very much because you're farther away from it. But let's think about what's happening from this charge way out here. It's now creating an electric field that's in this direction. And the one down here is creating an electric field that's in this direction. Now they're smaller, right? They're smaller. But because of the angle, they don't cancel each other out as much. So we get the y components cancel, but the x components don't. And those x components are a little more significant now than they were when we were close to the wall because the angle was so steep there. And it turns out that the electric field, all this stuff adds up and gives you the exact same electric field you had here. The electric field is constant. I want to make one more point before we close out this video, and that is that this is an insulating sheet of charge. And if I take an insulator and I cover the side with charge, I get a certain sigma, and that charge stays there, and so that's the sigma I'm using. That electric field comes out in both directions, and I know what sigma is. It's a little more complicated when this sheet is a conductor, because when you put the charge on that surface, it doesn't stay there. You can't have a conductor that's so thin there's only one side to it. You always, no matter how thin you make your conductor, there's always a face on one side and a face on the other side. And when you put that charge on the conductive surface, it's going to split. Half of it's going to go to one face and half of it's going to go to the other face. And so the sigma is different. Sigma is charge per unit area on one side of the conductor, not both sides, on one side of the conductor. So if I have a sigma for an insulating sheet, an equal sigma for a conductor would be half as much, because it really has charge on both surfaces. So if the sigma was 10 coulombs per square meter on an insulator, to get the same electric field from a conductive sheet, I would need 5 coulombs per square meter, because there'd be 5 on one surface, and then if I flipped it over and looked at the other surface, there'd be another 5 over there, giving me 10. But we'll talk more about that in the next video.